Imagine you're working for a company and this company has a server for file management. You need to be connected to this server if you want to access or modify the company files. Because you and other employees are connected by this same server, you have access to the same company files. Let's say you make a new file called hi.txt and you save it in this file server. This file then gets uploaded to the server and is synced with the other computers in this server. This means that other people will be able to see a file called hi.txt among their company's shared files. When other employees want to open the file, this version of the file that you saved then gets downloaded onto their respective computers. One of the roles of a file server is to ensure that the file last modified by one person is the same throughout the rest of the server. In our case, our text file hi.txt should be the same as the state that you saved it in when employee A accesses it. So how can we verify that the file that you uploaded and the file that others download are exactly the same? To simplify the problem, let's just focus on the download process first. The simplest way to do this is a character-to-character mapping. This is achieved by comparing each letter from the start of the file to the end of the file and checking that it matches. You probably realize that this method is extremely slow, as we'll be doing as many computations as the size of the file. If there is a way to minimize the number of computations, it will be using a hash function. Once a file is saved inside the server, we will first pass its file name and its file contents into a hash function. A hash function has a number of properties, but essentially, they transform an input of varying size into a fixed size output, and it has a unique output for every input, or a one-to-one function. The output of a hash function is called the hash digest, and it is stored in the file server. When employee A decides to access the file, both the file and the hash digest is downloaded from the server into the computer of employee A. Before granting employee A the access, the computer will first compute the hash of both the file contents and the file name in a similar way done in the server. This is to verify that the computed hash in employee A matches the hash downloaded from the server. In this case, we managed to verify that the two hashes are equal. This means that the contents of the file are exactly the same on employee A and the file server. So, what do we achieve by using this hash function? Firstly, because the output is of fixed length, we are able to check that this is exactly the same file in a constant number of operations. This doesn't depend on the size of the input because the hash digest has a fixed size output. However, there is still a problem that is not solved. What happens when a file gets corrupted during download? Suppose that there is malware during the downloading process of the file and hi.txt is corrupted. Then the hash digest will be different from the original hash that was downloaded from the server. The server will then proceed to re-download the file again and repeat this process until the file integrity is assured. This is where the disadvantages lie. We are required to replace the entire file because we have no information about the location and the extent of the file corruption. For instance, suppose that our hi.txt file is 1 TB in size. If malware modifies a single byte of this file during download, we will need to re-download the entire 1 TB of file without any guarantee that this new file is not corrupted. This will severely impact the bandwidth of our company network. Big question. In a distributed file system, how are we able to maintain file integrity across all clients in the network, but at the same time being efficient computationally and utilize as little memory resources as possible to optimize our network performance? The answer is Merkle trees, and let us give you an intuition behind this structure. Before we come to understand Merkle trees, first we need to understand the idea of a graph, which looks something like this. Essentially, graphs are just a way that we represent and conceptualize information. This is how a network graph looks like in computer science. Graphs have nodes that contain some form of data about itself and also contain edges, which are essentially links to other nodes. There are different types of graphs in the study of graph theory, but essentially the idea is still the same, that nodes contain data and the edges are links between the nodes. Another application of graphs will be picturing 4 towns connected by some form of road network. We are interested in the leftmost structure, and it is called a tree, which has 2 properties. 1. The graph is connected, which means that there is a path from one node to every other node, and 2. It's without cycles, unlike the road network on the right. This is where Merkle trees gets its name. Merkle trees are used by distributed file systems to check the integrity of the file upon upload and download. Distributed file systems are a set of clients and servers. A client refers to a device that accesses the file system. An example of a client would be those individual computers distributed to employees of a company. A server refers to a device that manages and stores files, allowing clients to access files in the file system to upload or download files. An example of this will be the file server of a company where all company employees are able to access these files. Merkle trees are used in distributed file systems. Every file in the server's file system is often split up into non-overlapping chunks of data packets. In the example on the left, a 10GB file is split up into 4 2.5GB data packets. These file chunks are non-overlapping and each file chunk has the same size. The data inside the leaf nodes of the Merkle tree, which is the lowest level of the Merkle tree nodes, is created containing a hash that is computed from each individual data packet. Next, a parent node is created containing the hash that is computed from two adjacent child nodes. What is actually passed into the hash function at this point is the concatenation of the two hashes below it, otherwise called its children. Finally, this process is repeated until the Merkle root is reached, containing a hash that is computed from all the child nodes in the Merkle tree. With this, a Merkle tree is formed from a file in the server's file system. This process, from the separation of a file into individual file chunks and the computation of the hashes from the leaves to the root, is how a Merkle tree is built inside a file server. Now, let's examine how we can detect data corruption using this structure. The diagram on the left represents an already constructed Merkle tree in the file server. Now, let's imagine that a client wants to download a file from the server that so happened to be corrupted by malware, and it modifies data packet 4. Due to the error present in data packet 4, a hash value E is formed instead of the hash value D. This leads to a cascading effect where the hash values of its parent and all the nodes above it up to the Merkle root are compromised. Finally, at the root node, a hash value of ABCE is formed instead of a hash value ABCD, which is a mismatch between the client and the server. This means that somewhere down the tree, there was some error during the file download. In order to detect which data packet contains the error in the file, the hash value contained in the client's children nodes will be compared to the hash values contained in the server's corresponding nodes. First, the server's hash value AB and the client's hash value AB are compared, and since they are the same, there is no data corruption in the client's HAB node and its child nodes, so there is no need to check the rest of the subtree rooted at hash AB. Next, the server's hash CD and the client's hash CE are compared, and since they are different, there exists data corruption somewhere in the subtree rooted at hash CE. And we can follow this pattern of checking the client's children nodes with the server's corresponding nodes to eventually discover the error at data packet 4. With this knowledge, the server is able to resend data packet 4 without having to resend the entire file, conserving the bandwidth of the network as well as time. After the server resends data packet 4 to the client, the Merkle tree is formed again from the newly corrected file in the client's file system. Then the hash values contained in the Merkle root of both the server and the client are compared. If these hash values are the same, it means that there is no more data corruption, indicating that the integrity of the updated file is restored. So far, we've talked about 3 methods of attaining file integrity, but of different levels of optimization. We can classify these methods with respect to the number of computations required and space efficiency. The first method we discussed is inefficient in both the number of computations and space, because we'll be doing as many computations as the size of the file, and if there is any error, we will need to replace the entire file. Next, the second method is very computationally efficient because the algorithm involves the computation of just 2 hash functions, but is inefficient in space, in the worst case when the file is corrupted. Merkle trees are slightly less computationally efficient than method 2 because the number of times the hash function is computed is equal to the number of nodes in the tree. However, it does significantly improve space efficiency. Now, let's consider a file system that uses Merkle trees. Before going straight into how DataStax Enterprise use Merkle trees in operations to repair their nodes to ensure data consistency and maintenance, we must first know what a NoSQL database is. So a NoSQL database, also known as a not only SQL database, is a database that manages unstructured and semi-structured data. Apache Cassandra is a NoSQL database, written in Java, that provides unique utilities that cannot be matched by other NoSQL databases. It is an open source, distributed, and decentralized storage database for managing very large amounts of structured data spread out across the world. DataStax Enterprise, which is built on top of Cassandra, provides an anti-entropy repair tool. Entropy refers to the replica data that is not in sync, because the current data is outdated. Replicas refer to the duplicate of the original files. And thus, anti-entropy refers to the synchronization of replica data to ensure that data is updated. Anti-entropy repair has two phases to the process. Firstly, a Merkle tree will be built for each replica. Secondly, DataStax compares the Merkle tree to discover the differences. The leaf of a DataStax Merkle tree is the hash of the raw data. It has the same structure as other Merkle trees. Every node higher up in the tree is a hash of its respective children. It's because of this structure that Cassandra can check each branch independently without needing to create a copy or a replica of the entire file. Consider what happens when there is a difference in file versions. This time round, the file is not corrupted by malware or anything, it's just modified, like you editing a Google Docs or something, and your changes being saved across all computers. If a difference is detected, the differing nodes exchange data for the conflicting ranges and replaces the data in these ranges with the new file version. However, data is always changing. How can we ensure that the changes that one replica sends to another will be still valid by the time they travel over the network? DataStax uses something called SS tables, which are crucially unalterable states of file. Because data is always being constantly updated, the new data is written into these unalterable states of file and are used for Merkle tree comparison processes, from the hash computation to the Merkle tree comparison to the updating of old files. This is to tackle the problem of ever-changing data. In summary, a Merkle tree is just a tree with nodes and edges. Each leaf node is a hash of its children nodes. A Merkle tree is built from the leaves up to the root and detects data corruption by comparing hash values from the Merkle root down to the leaves. One of the many applications of Merkle trees would be in the DataStax Enterprise, where they are used to check whether replica data is in sync with the original data and will update it if it is not. Thank you for watching the video. We hope you enjoyed it.